And our next speaker is Cotte. Marine is beamline responsible of ID21 beamline at the ESRF in France. And she's going to talk about nano-spectroscopy in the tender X-ray domain. So the stage is yours, Marine, please.
Thank you, Eva. I hope you can hear me well.
Yes, we can hear you. We can see your presentation and the pointer as well.
Super. So I also hope that my computer will be efficient enough. So first of all, many thanks to the organizers and Jakub in particular for the kind invitation. I think it's not so often that we have this kind of discussion about nano-spectroscopy or microspectroscopy in the tender X-ray domain, and I'm very, very looking forward the presentation and discussion today. So ID21 was built in the 90s already with the idea to offer spectroscopy in the tender X-ray domain. And over the last 5 years, we benefited from an important refurbishment. So this is something I will present during my talk. So first, if I can switch to the next slide. Okay, oops, sorry. So first of all, let's a short presentation of the beamline team who takes care about the maintenance, development, and the operation of the beamline. Something which is, I think, interesting and a bit particular for ID21 is the scientific communities. So here you have a graph showing the statistics over the ESRF, where with the very important scientific domains such as hard condensed matter science, applied matter science, chemistry, structural biology. And if we make a zoom only on ID21, you see that we have users who are coming from very, very different fields and not the main ones. So in particular, earth science, life science, medicine, environment, and cultural heritage as well, which is an important activity at the beamline. So I think this is a peculiarity of the microspectroscopy beamline in the tender X-ray range, and which should be considered probably for the future Solaris beamline. So a few, let's say, trends or keywords for these 5 main scientific topics. So in cultural heritage, the 2 main questions are, can we get information, insight about masters' secrets? And on the other hand, how and why artworks degrade in some cases. We also, environmental science is also a very, very important field where usually we are interested in the fate of manufactured materials in the environment with sometimes positive and sometimes negative impacts. And other examples are the accumulation of metals in plants. Health is also a subject where we are interested in the interaction of manufactured and biological systems. For example, the case of tattoos, drugs, implants, and so on. And we also have research or experiments dedicated to understand biological phenomena. For example, chemical modifications induced by the neurodegenerative diseases. Earth and planetary science are important as well, where users will use X-ray fluorescence and spectroscopy to get chemical signatures, and such that they can get information or deduce information about geological processes or also study paleoclimate. And maybe 5 or 10% of our activities are dedicated to manufactured materials. For example, as shown here, solid oxide fuel cells, and where users are interested in what happens at surfaces or interfaces, and with notably diffusion of elements or chemical reactions at boundaries. So to fix a bit the idea, so globally, the users, they want usually to have both identification and location of chemical markers in complex materials. So to show you in practice what it means in experiments at ID21, I have chosen 2 illustrative case studies in 2 domains which are important at ID21. On the left, cultural heritage, and on the right, environmental science. In these 2 cases, users were interested in cadmium. On the left, this was about the degradation of cadmium yellow pigments in the screen. And on the right, the fact that regulation evolves and that in some countries, the natural level of cadmium is too high and creates a risk of problems with respect to contamination of cadmium in cacao. So these are the key questions. How does cadmium yellow degrade in the screen, and what is the cadmium path from the soil to cacao beans? So this is how experiments will run usually at ID21. Users, they come with fragments. So we did not bring the full screen, but only a fragment of it. And on the other end, we add cross sections or thin sections of cacao seeds. And then we start with 2D microfluorescence map, such that we can identify and locate elements. So in this case, sulfur and cadmium. And on the other hand, we see where is cadmium, how deep it penetrates into the seeds. Just to let you know that we don't offer 3D mapping. And the second step is usually to tackle the chemistry. So this can be done using xanes typically. So here you have examples of xanes at the sulfur K edge, where we can see that depending where you are on the paint fragments, the signal is not the same. And in addition to the original cadmium sulfide, which is a pigment, we observe also agglomerates of sulfates. And in some cases, we can go further and try to map these different species. So in the case of the Munch cadmium yellow, what we did is that we acquired the same map at 2 energies, which are shown in red and green. So this is multispectral mapping, but in the future, this is something we would like really to stabilize and make more efficient by increasing the speed such that we can acquire these kind of multi-energy maps at tens or hundreds of energies. So in summary, the link between these two examples is the fact that we have a lot of non-expert users who aim at identifying and localizing various species from major to trace elements. Also, something which is important is that the samples usually contain both low-Z elements like phosphorus, sulfur, and metals, usually in biological matrices, but often complex and heterogeneous, and so they need submicrometric resolution, but still large field of view in the range of submillimetric range. So here you have the elements which can be detected. So these are the ones which are in color, and the ones which are in bold as those for which we can do absorption spectroscopy. And then here I summarized a couple of applications to cultural heritage. So with the case of cadmium yellow, globally, the common motivation or objective is to understand why some pigments or some materials under specific conditions like light, temperature, or humidity, they degrade. And we use fluorescence to identify elements and xanes to get information about these chemical reactions. So other examples are degradation of chrome yellows, of smalt, of emerald green, or also not talking about degradation, but understanding the composition of some components. We analyzed the support of Leonardo's codex. We also analyzed inks in papyrus and different chemical products used for the consolidation of limestones. So this shows you how diverse can be the cases. And if I switch to health and environmental science, you will see as well that we tackle many scientific problems. So for example, here you have many analyses where users were interested in the location and speciation of 3D transition metals in various biological systems, like in agriculture, in soils, also asbestos in lugs, and so on. But beyond 3D transition metals, we can also study many heavier metals, such as silver, cadmium, indium, tin, and so on, thanks to their L edges. And I think this is something which is very interesting in the tender X-ray domain. So this is a sketch just to, I would say this sketch represents about half of the experiments that we do at ID21. We usually have a biological system which is interacting with the exogenous, usually manufactured materials, and we want to understand how the biological system reacts and how also possibly the exogenous material is concentrated, is modified from a chemical point of view, and so on. And this both in the case of intentional use or in the case of incidental exposure. This is a sketch of the beamline as it was in 2016, and probably a bit similar to what Jakub saw when he was a postdoc with us. So at that time, in 2016, we had 4 stations. The main one was scanning X-ray microscopy in the tender X-ray range, at that time from 2 to 9 kV. We were also offering xanes in full field mode, a station for microdiffraction, and the infrared microscope. So at that time, we were invited to think about the future of the beamline and the refurbishment and what was the strategy for investment in terms of budget and resources. And we decided to concentrate on spectral microscopy with several objectives. So to extend the energy range, to make the switch from cryo to room temperature easier, to get a smaller beam, to better collect its reflorescence, and to keep micro X-ray absorption spectroscopy as a key technique, but extended to 2D whenever possible. So the refurbishment was split into 3 parts. The first part was about the primary optics and optics hutch. The second part was the installation of the first prototype of new double crystal monochromator. And the third part, which is still ongoing and finishing now, is the installation of a new nanoscope. So this is a sketch of all the things which happened since 2018. So the first part was ended in 2018. We got the DCM just before the ESRF was closed, so it was a bit frustrating because we had to wait for the beam to come back to continue the commissioning of the monochromator. We had the first EBS users in 2020, and then we had the second shutdown for different installation in the experiment hutch. We took the beam back in 2022, and the nanoscope itself was installed in 2023, and we spent last year installing different parts in it, and the first beam was taken in the nanoscope in December. So some major technical achievements which were achieved in 2018, 2022. So as I was mentioning, we are the first beamline benefiting from this new generation of double crystal monochromator for spectroscopy. The purpose being to have a beam as stable as possible, both in static and in dynamic conditions. There is a huge upgrade or migration of the control software from spec to BLIS. So ID21 was among the first. Something which is very important for us is graphical user interface. If you have in mind our users coming from cultural heritage, from environmental science, they need to have a microscope which is, I would say, as easy to use as an optical microscope or electron microscope. And this is possible thanks to daiquiri or graphical user interface. And also something I think which is highly appreciated by our users is all the work which has been done or which is still being done for data policy, notably electrical logbook, the data structure, metadata structure, to make things as automated as possible and as user-friendly as possible. So even if the refurbishment is not completed now, we can already see impacts or improvement compared to before EBS. So notably, the fact that we have now the new EBS source, the flux is much higher. And the example I showed you about cadmium in cacao is only possible because we have an increased flux offered by EBS and also because we are pushing further our X-ray fluorescence detector. On the other hand, when we are working on nanoparticles, XENS on nanoparticles, without the present monochromator, it was very difficult to get good XENS spectra on nanoparticles because even if the beam is small, it's like 0.3 microns vertical, 0.8 horizontal. If the beam is moving over 1 micron and you are trying to scan a nanoparticle of 100 nanometers, you will get this kind of structures which are just artifacts. So we had a solution which was a bit turning around in the past by acquisition of maps, but now that we have the new monochromator, the beam is stable enough so that we can stay centered on nanoparticles and that we can get decent XENS spectra also on nanomaterials. So briefly, what will offer the new X-ray nanoscope? So we have kept the historical scanning X-ray microscope, in particular for the study of larger samples which do not require an ultimate resolution. Both nanoscopes operate in the same tender X-ray range from 2 to 11 keV. The two main techniques are X-ray fluorescence and X-ray absorption spectroscopy. But as I was saying, by increasing the speed, we hope to make multi-energy maps as accessible as possible. We always work under vacuum, and we can work either in cryo condition or at room temperature. Now, what are the differences between these two instruments? So as I was saying, we keep the old microscope for unfocused beam or medium size. And with the new nanoscope, we hope ultimately to reach a beam of 100 nanometer. But now we in December, we reach a beam of 200 nanometers, which is already very good. In the old microscope, we have only 1 kb, which is coated with nickel. This is very good in the range 2 to 8 kb, but above the nickel K edge, the flux is not that good, and also we cannot do nickel xenes. So this was the reason why we have now in the new nanoscope 2 kbs, one coated with nickel and the second with platinum, such that we can give a very high flux over the entire energy range. And also something which will be very, very important is the fact that in the past, we had only a single element X-ray detector, and with the new nanoscope, we will have 5 elements X-ray detector, meaning that the detection of the fluorescence will be much more efficient. So what are the directions for future development? So first, the priority is to complete the commissioning of the new nanoscope, and this is really ongoing. And then as soon as we make it available to users, for sure, we will have to work on developing different sample holders to get them easy to use and to switch from one station to another or one beamline to another. An action we started about 5 years ago, and which is also super important, is to consider that provide users with data is good, but if they are not able to process this data or analyze this data, all our work is useless. So there is a huge action at the ESRF towards data analysis as a service, and notably the development of workflows. And so this is something that we want really to push forward in the future. And also something which is important that our management is pushing us as much as possible is to increase the transversality among beamlines and not to stay focused at the level of beamlines. And with this, I will thank you for your attention. I'm very happy to answer your question, and I thank all our users and colleagues involved in this research.
Marine, thank you very much for this great presentation and information about the refurbished ID21 beamline. And maybe we have time for one question because we are late, a little bit late. And is there any question? I can see already. Alexander Kordiuk, yes, please.
Okay, I just wanted from point of view physics, condensed matter, and about cryostage. Cryostage, yes. What is the reason for you to use cryostage? What's the main motivation, and which temperature it's allowed?
Yeah, so it's a liquid nitrogen cryostage. Typically, this is for biological samples. That if you want to get first to want to preserve your sample, but also that your xane spectra are not too much modified under the X-ray beam, it's much better to work in cryo conditions.
Okay, have you seen the examples of using your equipment, your beamline for let's say investigation of the samples under current, for example, electrical current? For example, it would be interesting. I could imagine to investigate memristors, for example, about the distribution of the diffusion of some elements. Is it
so this is not possible at ID21. We have very limited in situ, let's say, conditions, basically only cryo. We do not offer fluid capabilities, or we did in the past, but very occasionally the design is not relevant or is not adapted for this kind of in situ experiments. But this is probably something which should be taken into account for the design of this new Solaris beamline, because these are the things you should consider from the very beginning to make sure that everything around the sample is optimized for this kind of in operando or in situ experiments.
Okay, thank you.
Okay, there's one more question from Małgorzata Makowska. Yes, please.
Thank you. So I just wanted to ask about your monochromator. So I didn't get it. Is it horizontal or vertical?
Vertical.
Okay. And then this great stability that you have within 1 micron, do you have some position feedback to the monochromator, or is it really just what you get
The way we use it is based on interferometers. So we build basically calibrations. So we start a calibration of the monochromator by observing the beam position and by building tables such that you try to keep the beam as stable as possible. And then you use this table to somehow to correct the position and distance of the second crystal with respect to the first one. This is not, but then this correction is not, you don't measure the beam position in real time, but you measure the crystal position in real time thanks to interferometers. So you make the hypothesis that the calibration you have built and the table you have built is stable over the time. But ultimately, there could be an online feedback based on beam position. But at ID21, we cannot measure simultaneously the beam position and the sample signal. So we make the hypothesis that the beam drift is stable, which is in the main drift is indeed repeatable.
Okay, thank you.
There is one more question from Luc Cotte. Yes, please.
Hello, thank you. Thank you for Marie for this very interesting, impressive talk. I have questions for the new beamlines. Did you use completely new insertion device, or you still have this? I think you had this Wiggler 80 and ondulator 40 and 42, or what is the situation? Can you?
But after the EBS, many beamlines kept their previous ondulators. In some cases, I think the straight section was too short, so some users had by default to change their ondulators or insertion device because it was no longer fitting into the geometry of the source. At ID21, we did not make any change. But I know that there are many beamlines, for example, which are going towards in vacuum ondulators or cryo ondulators.
Yeah.
So, but I mean, there is no single answer to your question. But for what we are concerned, we kept our ondulators, which are pretty good.
Okay.
Yeah.
Okay, good. This is what I wanted to know. Thank you.
Okay.
Okay, Marine, thank you very much for your presentation. And now we move on to the next presentation, which will be given by Delphine